Good afternoon. Let me welcome you to the second event in the Four Color Fest. Let me remind you, after today's lecture, there is a reception from 5 to 7 in Alice Campbell Alumni Center, which is the building directly behind this one. You can't miss it. And the events tomorrow are the IGL Lab, which will also be in that place, from 10 to 12, and the concert, A Portrait in Four Colors, which will feature an original composition by Rudolf Haken, and a virtuoso display of the Haken fingerboard continuum. So it's a great pleasure today to introduce our speaker, Andrew Appel, who's Eugene Higgins Professor of Computer Science at Princeton University. He was chairman of the department from 2009 to 2015. He is a fellow of the Association for Computer Machinery. He's the author of several books, such as Modern Compiler Implementation in ML. I found out what ML is today. He's the author of over 120 papers. He has had 21 PhD students. His main interests are software verification and machine proofs, computer security, and technology policy. He's well known in the latter category for his work on the security of voting machines. I understand that progress is being made in the New Jersey legislature. And today he will talk about graph coloring and machine proofs.
Or can it really be a proof if you can't check it by machine? And I'll start with Alfred B. Kemp, who you heard about yesterday. In 1876, he proved Kemp's universality theorem. So here's a linkage system. It's got some things pivoted to the plane and other rigid bars pivoted to each other. And here it shows that one of these pivots is tracing out a straight line segment, right? So from only pivots, you can get straight lines. And he proved that any algebraic curve can be drawn by one of these pivot systems, except that his proof was invalid. So it was proved 26 years later by Kopovich and Milson. That's not your Professor Kopovich. That's the brother of your Professor Kopovich. Okay, so no problem. He moved on to prove the four-color theorem, that any map can be colored with no more than 4 colors. Here I draw the maps in the sort of graph theory style where you color the nodes and there are interference edges. So, but of course, there was a bug in that proof too that was found, as Robin Wilson explained to you yesterday, by Percy Haywood. So let me talk about Alfred Kemp's graph coloring result, because it actually continues to have importance in computer science today. And here's a theorem. Every planar graph has at least one node of degree less than 6. That's provable from Euler's formula about the number of vertices and the number of edges and the number of faces in a graph. So the average degree of the nodes must be less than 6. So there must be some node of degree 5 or less. And if you remove one node from a planar graph, the result is a planar graph, because you're only taking away stuff. And this leads to an algorithm for coloring graphs. So here's how do you 6-color a planar graph. Every planar graph has at least one vertex of degree less than or equal to 5. And remove this vertex. Color the rest of the graph recursively with a recursive call to this same algorithm. And then put the vertex back. And when you put it back, it will be adjacent to at most 5 vertices, which use up at most 5 colors from your palette. And so you can use the 6th color for this vertex. So here's an example. Node C has degree less than 6. Remove it. Now, by induction, color the rest of the graph. And then when we put node C back, we can certainly find a color, because it's only adjacent to 5 other nodes, so they can have at most 5 other colors between them. And so we can use the 6th color to color node C. OK. Now, so that was straightforward. That's how to 6-color a planar graph. Here's Kemp's 4-coloring algorithm. So if you find a node of degree 1 or degree 2 or degree 3, you can use the algorithm I just showed you. For degree 4, you can use the method of Kemp chains. So here's, oops. there we are, the method of Kemp chains. Suppose when you put node K back, it's adjacent to nodes of 4 different colors. So then take node D and recolor it red. But that means you need to recolor node K green. And then you have to color this one red and this one green. And if it chains all the way back to node J, then that didn't work. But if that happens, then there can be no chain of blue and yellow between G and B. So that's the Kemp chain argument, and it works just fine. So to prove the 4-node case, you use Kemp chains. And then to prove the 5-node case, it's very straightforward. You just use the method of simultaneous Kemp chains, which is unsound, as shown by Haywood in 1890. OK, so Kemp really did end up successfully proving the 6-color theorem, because that method works to 6-color graph. And Haywood really showed in 1890 that the 5-color theorem is sound, but the 4-color theorem was not proved for a while. And during the 20th century, the method of unavoidable sets was developed. So this history of unavoidable sets is from a paper by Appel and Hawkins submitted in 1974, and it's not my father's handwriting, so it must be Wolfgang's, I think. And it shows that Franklin had this unavoidable set. So that set by Franklin, every planar graph must have one of those configurations in it. And if you could find a way to somehow remove the configuration, color the rest of the graph, put it back, Kemp chain the thing, then that would be a proof of the 4-color theorem. But unfortunately, not every configuration in Franklin's unavoidable set was reducible in that way. And Lebesgue had another unavoidable set in 1940. Heisch had an unavoidable set in 1969 with 25 configurations in it, almost all of which were reducible. And then in 1970, Heisch had an unavoidable set of 8,000 configurations that looked like they might be reducible, right? So this was the progress up to 1970, that if you could find an unavoidable set of reducible configurations, that would prove the 4-color theorem. And so Heisch said, well, someday computers might be powerful enough to find an unavoidable set of perhaps 10,000 reducible configurations. OK, so Kenneth Appel and Wolfgang Haken in 1972 decided to estimate how many configurations might be in an unavoidable set of reducible configurations, and in what year will future computers be fast enough to calculate this. And they concluded in this paper they submitted in 1974 that it might be about 2,000 configurations. And the year in which computers would be powerful enough to do it was 1972. Well, OK, so then they got to work. And between 1974 and 1976, they calculated an unavoidable set of approximately 2,000 configurations. And the reducibility proof for each configuration is a case analysis on about 200,000 cases, right? So for a configuration of ring size 14, as Robin Wilson explained yesterday, you need to sort of case analysis over 14 quantified variables of 4 colors, and it's a big case analysis. And you can't write that down by hand, and you don't even want to print it out from a computer, but you could have a computer program which my father, along with John Koch, a computer science graduate student, wrote in Fortran and IBM assembly language that would check the 200,000 cases for each of the 1,936 configurations. And a lot of the work was done. My father used this teletype ASR33 terminal. This is an electromechanical printing terminal connected by telephone from Southeast Urbana to the university computer on campus. It communicates with the central computer at the rate of 110 bits per second. So if you're used to 50 megabits per second, then just divide by, 500,000 or something, and you get the idea. And it's very loud. It was sitting right under my bedroom in my father's study at all hours of the morning. In April Fool's Day of 1975, about halfway through that second 2-year period, the mathematical games column in Scientific American had this map that Martin Gardner put in his mathematical games column and said, well, a 5-color map has been found that can't be colored with 4 colors. And when that arrived in the house in the mail, my father went down to his study, and he did not come out until he had colored it. Okay, so in 1976, Appel and Haken completed the proof of the 4-color theorem based on approximately 1,900 of these configurations. And as Robin Wilson explained, the dark dots indicate nodes of degree 5, and the simple vertices are nodes of degree 6, and the unshown edges are out to the ring, and so on and so forth. And there's a reducibility argument for any possible coloring of the ring. The computer program could calculate that you could replace this configuration with a smaller one, and then when you have to put it back, you can recolor in such a way that you can find colors for the nodes in the configuration. And then famously, the postage meter of the math department of the University of Illinois advertised this big result on their postage meter back when first-class postage was 13 cents. And Robin Wilson reported that the various Appel and Haken children spent many hours proofreading the configurations. With apologies to Robin Wilson, he was misinformed. It was only 2 of the children, Laurel Appel and Dorothea Haken, that did all of this work, really. The boys slacked off and hardly did anything. Okay, so what does it mean? The computer printed out lists of numbers. It didn't have a graphic printer that could print out configurations like this. So they had to check that the list of numbers corresponded to the configuration, and that the configurations proved reducible corresponded to the configurations in the unavoidable set. And so Laurel Appel, age 13, and Dorothea Haken, a couple of years older, spent months correcting typographical errors and bringing the more serious errors to the attention of their fathers. And by around the middle of July, the proof was completed, and the checking of the configurations was completed, and the result was announced. And then the mathematicians went around the country giving talks about the result. And Armin Haken, who was then a graduate student at Stanford, gave a talk explaining how the result worked. And, the people under 40, the people over 40 couldn't believe you could trust that some computer calculations could be a proof. And the people under 40 couldn't trust the part that was 700 pages of hand calculations and lists of configurations. So that's one history. It's sort of the history of the 4-color theorem. And it continued in 1996. Robertson and Sanders and Seymour and Thomas redid the Appel and Haken proof with only 600 configurations and a sort of improved version of the same basic recipe. And then I'll talk later about Gontier in 2006. But there's another history, I want to tell, which is about computing and calculation. So Leibniz's dream was, can we mechanize mathematics? And Babbage started trying to mechanize calculation. And Hilbert was really interested in mechanizing proof so that you could just turn the crank and get the proof out for your theorem, or the definite information that the conjecture is not true. And so Gödel in 1929 or so, 30, demonstrated that there's some problems there. And Turing in 1936 demonstrated that there are no decision procedures. And in the process of demonstrating that, Turing had to invent computers, the concept of general purpose computing. And And a consequence of Turing's result is that there must be some short theorem statements whose smallest proof is actually quite long, which is, noticeable. So then von Neumann and others, Univac, Honeywell, IBM, started building computers, which was useful to people trying to prove the four-color theorem. And in the 1970s, there are two parts of computer science that I want to talk about. One is at IBM Research, having to do with optimizing compilers. And the other was at Edinburgh, having to do with logic and proof. So John Cocke was one of the most influential computer architects of the 20th century and one of the most influential compiler designers. So the compiler is the thing that translates your source program, your Fortran program, or whatever, to machine language. Cocke was a member in the 1960s of the team that built the Fortran H, the IBM Fortran H optimizing compiler, which was actually used by Appel in the four-color theorem. And one of the problems in writing an optimizing compiler is register allocation. So here's the register allocation problem. On the left, you have some program with variables, G, H, F, E, M, and so on. And on the right, you have the resources of the machine. You have some small number of fast registers and a large number of slow indexable memory locations. And you want to decide which variables to keep in registers and which variables can go in memory. And so Ashok Chandra, having seen these talks about the four-color theorem and Kemp's algorithm for coloring graphs, and said, well, maybe graph coloring is a good abstraction for the register allocation problem, and maybe we could color those graphs by finding low-degree nodes and removing them and coloring the rest of the graph and then putting them back. So he asked Gregory Chaitin to do it, and Chaitin says, I didn't know about this stuff. My field is information theory, really. But Ashok Chandra suggested to John Cocke to ask me to do this coloring algorithm. And of course, everybody at the time knew about the Appel and Haken result. So this was one of the most influential papers in the field of computer science, register allocation via coloring. That register allocation can be viewed as a graph coloring problem, and two nodes are connected by an edge if the quantities interfere with each other, that is, if they are simultaneously live at some point in the program, and that the algorithm you use for coloring the graph is Kemp's algorithm for 6-coloring a planar graph. So here's live ranges. The variable G is defined at the second line, and I have an inaccuracy there. It's used in the fourth line. So the live range of G is only from line 2 to line 4. The live range of K is from line 0 to line 3, roughly. And then it's dead for a while, and then it's live again down below. And if two variables are not live at the same time, you can put them in the same register. The register can be representing one variable for a while and then another variable later. So Chaitin's abstraction was to understand which pairs of variables interfere with each other, that is, their live ranges overlap, and then to construct an undirected graph with an edge between any pair of nodes, variable names, whose live ranges overlap. So that's the interference graph. I'll talk about the dotted line edges later, but just look at the solid edges. So there's a graph. Now, these graphs don't have to be planar. There's no particular reason that register interference graphs are planar. And in fact, if you have lots of variables live at the same time, you could have 100 variables live at the same time. And so you've got a clique of size 100 where each node has degree 99, and there's no guarantee that there's a small degree node. All right, so here is Chaitin's heuristic hack of Kemp's algorithm. To mostly k-color a graph, whether it's planar or not, and k, the number of colors you have is equal to the number of registers on your machine. So some machines only have 4 registers, and some machines have 6 registers, and some machines have 32 registers, so whatever your k is. Is there a vertex of degree less than k? If so, remove this vertex, color the rest of the graph, put it back, and you will be guaranteed to find a color for the node that you put back. If there is no node of low degree, pick some vertex, remove it. That lowers the degree of several other nodes. Color the rest of the graph as best you can, and now you put it back. If when you put it back, it's going to be adjacent to, greater than or equal to k vertices. So if those vertices happen to have among them less than k colors, you'll be able to find a color for it. And if not, leave it uncolored. That's the great thing about register allocation. If you leave it uncolored, that means you're storing this local variable in memory, where it's slower, instead of a register where it's fast, but the program will still run. So we can get away with this simple hack. We don't even need Kemp chains, let alone simultaneous Kemp chains, which would have been a big worry. So here's how do you 3-color this graph? Okay, if I have a 3-register machine, find a low degree node, degree less than 3, remove it, push its name on the stack, right? That lowered the degree of node B and node M, right? Find a low degree node, H, remove it, put it on the stack. That lowered the degree of G. Now it has degree 2. We can remove it. Now, there's no low degree node. Every node has degree at least 3. So we'll pick a node. There's some heuristics for which node to pick, but it doesn't matter. We'll pick K, remove it, push it on the stack. This is actually Briggs's adjustment of Chaitin's algorithm. Color the rest of the graph, as I've shown. So we've pushed all the nodes on the stack, and now we can put them back in reverse order, coloring them. So each time we color a node, it's adjacent to less than k colored nodes, so we can find a color, except when we get here. This was the node that had, look, it's got degree 3 of colored nodes. But by a happy coincidence, 2 of them are colored the same. So we don't have to store this variable in memory. We can put it in a register. So we give it a color, finish coloring the graph. That's Chaitin's algorithm. And Briggs, in 1984, published an improvement of Chaitin's algorithm that does coalescing and improved spilling. Here's coalescing. Look at that assignment statement in the original program. D gets the value of C. We move C to D. Now, if we could manage to color C and D the same, that is, allocate them into the same register, then we don't need to have that move instruction, because the register is just moving to itself, and we can delete an instruction from the program. So these dotted line edges in the graph are coalesce nodes, move edges that we desire to color J and B the same if possible, and we desire to color D and C the same if possible. And Briggs reduction is coalesce a move edge, CD, so it is merge those nodes together if there's no interference edge from C to D, and if the coalesced node CD would have degree less than K. Because you don't want to remove moves at the expense of more loads and stores. That would be a disaster. All right, so that's Briggs's algorithm. Then Lal George and I published an improvement to Briggs's algorithm that interleaves the coalescing operations with the Kemp reduction operations, and also introduces another form of coalescing, which I call George reduction, because Lal invented it, not me, which you can coalesce C and D if there's no interference edge, and if the neighbors of D are a subset of the neighbors of C, then you cannot be increasing the chromatic number of this graph by doing that. Okay, so that's our version of Briggs's version of Chaitin's version of Kemp's algorithm. And we published it in 1996, and this is one of the most widely used algorithms in compilers today for register allocation. And if you use GCC or whatever, you're probably using this algorithm. Okay, that was fun. So that's compilers and computing. But let me tell now another history about logic and proof. So in the 1970s, Dijkstra and Floyd and Hoare became interested in how do you prove that a program is correct, program verification. And that is proofs by hand, of course. And then Robin Milner did something interesting. So Dijkstra and Floyd and Hoare had logics for proving programs correct. Generally, it's called Hoare logic now, but all of these people contributed. And Hoare logic was developed around 1970, 1971, so really contemporaneously with the four-color work. And in 1977 or so, David Grease, a professor at Cornell, wrote to my father and said, could I get a copy of your reducibility program so that I can prove it correct? So my father sent him a pile of Fortran and assembly language, and Grease said, oh, well, never mind. Because that program was not, well, not only was the program not really written in a style that it was easy to prove correct, but the technology, the science of proving programs correct was in its infancy in the 1970s. It just was not practical to do. In around 1978, so 77, 78, very contemporaneously with the four-color work, Robin Milner was interested in LCF, logic for computable functions. What kind of logic can you machine check about computable functions? And he built this thing called a proof assistant, Edinburgh LCF. And in a proof assistant, you use the computer, you construct proofs by hand, but they are checked by machine. Checking proofs by machine goes back to Gödel and Turing. And there's a programming language that comes with it, a tactic language that allows you to write little programs to help with the trivial parts. So that was very influential. There have been hundreds, well, maybe not hundreds, dozens of proof assistants built since then. I pretty much do all my research these days in a proof assistant. So let me demonstrate how a proof assistant works. This is the Coq proof assistant, developed in France from 1989 to the present. And here I have, at the top left, my program and proof script. And on the top right, I have the proof assistant tells me what I am required to prove. And on the left, I have a definition of the piano numbers, right? A number is either 0 or the successor of some other number. And I have a function I call add. It's a program. It takes a and b, which are natural numbers, and by case analysis on a, if a is 0, it returns b, and if a is the successor of a prime, then it returns the successor of add a prime b. So it's a recursive function, but it's well-founded recursion. It's structurally recursive on the structure of a, so it's defined. And then I can prove a theorem about this program. I can prove that add is associative. For all a, b, and c, add a of add b, c equals add of add a, b, and c. Everything in green has been accepted so far by the proof assistant's proof checker. Now I want to write the proof, because it says, all right, that's what you claim you're going to prove on the upper right. This is your proof goal. You must prove this. So I'm going to prove it by, to prove a quantified formula for all, I could say, well, let's assume I have arbitrary a and b and c. So intros, this tactic on the left that's just about to appear, I type in the word intros, period, and I hit enter, and it moves a and c and b and c above the line, and now they're assumptions. Okay, so I'll do induction on a. So this is case analysis on a. And here you see I've written the rest of the proof, but only the green part has been accepted by the proof checker so far. And as I press the button, so one step at a time, it will accept the rest of the proof. So the first case, add O, add BC equals add of add O, B, C. If I simplify the definition of add O, right, by its definition, you can see it returns the second argument. So if I call simple, as I'm doing right here, this is my remaining proof goal. It has simplified down to that add BC equals add BC, and this is obviously true. But obvious doesn't help. It has to actually be valid. But it is valid by reflexivity of equality. So I do that. Now, in the second case, the inductive case, I have add of successor of A, and so on. And if I simplify that by the definition of add, it simplifies to this, and then I apply reflexivity of equality, and, well, it turns out reflexivity of equality is invalid. One very important property of proof assistants is they will reject invalid proofs. That's the whole point. Okay, so I will undo that attempt at reflexivity, because I don't have equals here, and I'll rewrite by the induction hypothesis. IHA is the name of the induction hypothesis here, and it shows that for the smaller a, I could assume associativity. If I rewrite by that equality in the thing that's below the line, then this is my proof goal, and that is identical things on left and right, and that proves by reflexivity. So there's a proof in a proof assistant, and that's a machine-checked proof. And Robert Milner's observation, and that of many other people since, is machine-checked proofs are really good for theorems about computer programs. So one thing about a theorem about a computer program, the theorem is, here's a program, and it's correct. So that is, it has this observable behavior in terms of its input and output. Now, many theorems in mathematics are beautiful, and their proofs are instructive. But theorems about computer programs are usually, their statements are not beautiful. Here's this program, it's supposed to do that. That's not a very interesting theorem, although it may be a very useful theorem. And its proof may not be instructive. It may be long and have many cases, and no graduate student would want to have to referee that proof. And even a 13-year-old girl couldn't be convinced to check all the cases. But it's really useful in software verification, and software verification is what I do these days. So here are some landmark results in software verification. Xavier Leroy at INRIA built an optimizing C compiler that's proved correct in the Coq proof assistant. And he has just been named a professor in the Collège de France, which is an extremely prominent French academic position. Gerwin Klein in Australia proved the correctness and security of an operating system microkernel using a different proof assistant. And my former student, Zhang Chao at Yale, proved the correctness and security of operating system hypervisor kernel recently in the Coq proof assistant. And I've been laboring away in this field for about 20 years. I proved that a certain ML compiler generates safe machine language code in 2005. I have a framework for proving the correctness of C programs. I proved that a certain cryptographic authentication protocol is both correctly implemented and gives you a pseudo-random function with a certain guarantee, along with some colleagues, of course. So that's the third history of software verification. And if you have a proof of correctness of a program that's by hand, we don't believe it. Because by the time somebody finishes refereeing that proof, the program will have been maintained. So it's a different program. And proofs by machine, you can maintain the proof by machine along with the program, and you can check that the proof still corresponds to the program, and so on and so forth. Okay, 3 different histories. Now let's link them together. Remember, the under 40s could not be convinced that a proof that big by hand was correct. What is it magical about the under 40s in 1976? They were born after Turing's result. Turing's result was 1936. He showed what a computer is and what proof checking by computer is. And anybody born since then has been willing to accept that that's actually meaningful. So by now that's people under 80. Okay. So Georges Gontier said, why can't we check the entire 4-color theorem inside the proof assistant? Both the reducibility, which had already been checked by a Fortran program, but the Fortran program had not been proved correct, and the discharging, which had been done partly by program at some point and partly by hand. So his proof is entirely inside the Coq proof assistant. He has a program to do reducibility, just like Cage and Appel and Haken, but his program is proved correct in Coq and then runs in Coq, and he has the discharging proved correct, and so on and so forth. So here's the main statement of his theorem. First, so he does actual countries on the map. Of course, he pretty soon converts this to graphs, and he converts the graphs to something else, but his main theorem really is about countries on the map, and to define the map, to define the plane, you need what is a model of the real numbers. So he explains what is a model of the real numbers in about 100 lines of the logic of Coq, and then he defines what is a map, and a simple map, and the colorability of a map in about 40 lines of elementary topology written down in the language of the Coq proof assistant. And then he states the theorem for any real model and any M that's a map in that real model. And if M is a simple map, then it's colorable with 4 colors. And then the proof is 60,000 lines of calc, which can't have a mistake in it because every line of it is checked by the proof assistant, as I showed earlier in the slide. So that's a very nice synthesis of program verification with the four-color theorem. Okay, so if you were concerned, well, if you're under 80, so you were concerned that the by-hand part of the Appel and Haken four-color theorem might have a bug in it, you need not be concerned anymore, because there's a version of that theorem that's entirely checked by machine. Okay, let's unify computing with software verification and the four-color theorem. So a few years ago, I thought, you know, the one part of the compiler that is not formally verified is the register allocator. And I know how to do graph coloring register allocation. I published a paper about that. And I know how to do machine check proof. And wouldn't it be fun to write a paper in which I could cite some result from 1977 by Appel and Haken? So we just took the Kemp's algorithm, or rather the Appel and George version of the Briggs version of the Chaitin version of Kemp's algorithm for graph coloring with coalescing. And Sandrine Blazy of the University of Rennes and her student, Benoit Robillard, we proved it correct in the Coq proof assistant. So we merged those, and that was great fun. In mathematics, sometimes people even resort to machine-checked proof, even in the 21st century. So in 1990, well, Kepler in 1611, it wasn't originally Kepler, it was somebody else, but somebody else wrote to Kepler, and Kepler is more famous, said, the closest way you could pack spheres is this picture shown like you might stack a pyramid of oranges. And why were they interested in this in 1611? Because oranges weren't easy to find in Europe in 1611. They were interested in the atomic theory of matter. And these close packings are directly relevant to the atomic theory of matter. So Kepler conjectured that there's no denser packing than this. And it was unsolved for almost 400 years until Thomas Hales of the University of Chicago submitted for publication a proof, partly by hand and partly by computer, that had thousands of planar graphs, each with a computerized case analysis calculation. Does that sound familiar? Okay. And although a mathematician in 1976 could just barely get away with submitting a proof that had thousands of planar graphs with a big part of the proof by hand and a program that did some calculations on each one, the referees said, we pretty much believe this. We're 99% certain it's correct, but it's too big for us to have real confidence about. So its status as a proof was in doubt for a few years. So Hales decided, let's prove it correct end-to-end in a proof assistant, essentially just as Gonthier had been doing for the four-color theorem. So he did this. It took 10 years, and this is the team, right? Sometimes machine-checked proof is a big engineering enterprise. And if you've ever stayed to the very end of an animated movie these days, and you see the long list of credits of all of the engineers, this one animated the hair, and this one animated the clothing, and this one drew the sketches, right? This was the team. It's proved. You can't pack things any more densely than that. And everybody knows it now, even people under 80. Okay, so I'm pretty much done. Graph coloring, with or without proofs, is very useful in computer science. And it was brought to the attention of computer science by the big splashy result in 1976, the four-color theorem. But the algorithm we use really dates back to 1879, Kemp. Computer-checked proofs are widespread and important in computer science. So in my part of computer science, many of the sort of top refereed venues ask for machine-checked proofs. It's not always mandatory to submit them, but if you submit them, then the referees will actually examine the machine-checked proof to see that the statement of the theorem in the machine-checked proof corresponds to what you claimed in the paper, and then they'll run the machine-checked proof in the proof assistant. And This spring, in May or so, my student and I submitted a paper for publication, and it was about a certain compiler optimization algorithm, and we claimed we had a machine-checked proof, but we didn't send it in with the paper because there didn't happen to be a place in the submission form to do that. And in July, we got the referee reports and said, we are willing to accept this paper, provided that you immediately send us the machine-checked proof so that we can run it and check it, which we did, and the paper has been published. So it's part of the ethos of certain parts of computer science now that your proofs should be machine-checked. And I get advertisements, companies looking for jobs for industrial proof engineers. These are people that can formalize the mathematics of computer science for machine-checked proofs for, operating systems and file systems and compilers and so on. And computer-checked proofs are even sometimes becoming important in mathematics. Thank you. Coq?
Coq is 60,000 lines long?
No. Coq is the proof assistant, so it's the program that checks proofs.
Yes, but I mean the proof by Gautier that was still very long, right?
Yeah.
So whom do you trust more, that one or?
I trust the 60,000 lines because every line of it has been checked by the kernel of the Coq proof assistant, right? So the point of the machine check proof is that I can only construct valid proofs. That 60,000 lines is the construction of a valid proof. If I had a mistake, or if Gautier had a mistake in there, then the Coq proof assistant's kernel, the proof checker part of it, would catch the mistake. And so we need how to find the proof?
Yeah.
Oh, well, here's how Gautier did it. He read Robertson's paper. Okay, and the way Robertson did it is he read Appel and Hawkins' paper, right? So it's still mathematics. Turing proved that you're not going to be able to write a program that finds your proofs for you in general, but you can certainly check your proofs.
So is the proof checker, has that been run on itself?
So the question is, who has the proof checker?
The reason I ask is that in 1981, this was an assignment for a class. We had to prove a certain list program correct.
Right.
And I had a lot of trouble with that until I figured out how to prove 1 equals 0, or to get the checker to verify that 1
Right.
equals 0. And after that, it was...
Okay, so the question is, why should we trust the proof checker? Okay, so there's been a lot of work in that area. I've done some of it myself, actually. For example, in 2004 or so, I had a machine-checked proof done in the 12th proof checker. And I said, okay, under what basis do I trust the 12th proof checker? So what I did is first I read the refereed paper in the scientific literature that explained the logic underlying 12 and the algorithm for proof checking in 12, which was written by two of the most careful computer scientists I know, Bob Harper and Frank Pfennig. And then I said, okay, can I implement an independent checker using this algorithm as a computer program, and how long is that computer program? And the answer was 800 lines. So now I've reduced the problem to trusting that this 800 lines correctly implements that algorithm, and that the referees of that paper and the authors of it are trustworthy in that the algorithm is a logic that's consistent. Okay? And then you can inspect the 800 lines and the translation of that by the untrustworthy compiler to assembly language to make sure that just this once the compiler compiled it correctly. Okay, so that was a way that I could trust my big 100,000 line proof because it was checked by my 800 line proof checker, and the 800 lines is trustworthy because it's a clear transcription of an algorithm in a refereed journal. Okay, About 3 years later, Christian Urban said, all right, let's take that algorithm from the referee journal and check the proof that it's sound in a proof checker, a different proof checker. And he found a bug in the proof. It was a small bug in one lemma of the proof, and the theorem was still sound. So does that make us more confident or less? It makes me plenty confident. So there's lots of good research in representing proof logics in metalogics and proving the soundness of the metalogic checkers. There's always going to be some amount of circularity there. Nothing's perfect. But in many cases, we can have great confidence in these small programs that check proofs. Yes?
This is Victoria's son. You said something shocking that I think I must have misheard it. So you said, if I heard you correctly, that now when you publish a proof, it's customary to release the code, for example, or expect to have it checked by a proof checker as part of the publication process.
In the field of programming languages.
In the field of programming languages.
Which has higher standards of accuracy than mathematics.
Okay. well, okay. Let me read you something that I had a similar conversation with Tom Hales about 3 years ago. I'm looking at his email response now, and he's quoting the AMS ethical guidelines saying that mathematicians have a responsibility to publish full details of results that are announced without unreasonable delay. I would put the code in that category.
Okay. So about 4 years ago, the top conferences in my end of computer science decided to have an explicit artifact evaluation process. So if your scientific claim is based on a proof, you could submit a machine-checked proof script. If your scientific claim is about the high performance of some compiler optimization, you could submit the compiler and the test suite, which is not a proof at all. It's an experimental artifact. And the Artifact Evaluation Committee will examine the artifact to see that it relates to the claim being made and that it actually does run, and so on. And then the artifact itself is public. So that's how it works in scientific fields of endeavor.